To the section 7.2 video lecture for statistics at Morton College. I'm once again your professor, Dr. Scott Spaniel. And today what we're going to do is talk about applications of the normal distribution. So in the previous section, we looked at an introduction to what the normal distribution was and what the area under the normal distribution density function stands for. And so today what we're going to do is we're going to learn about how about the standard normal curve and how to do calculations on the normal curve. So go ahead and take out your note sheets, which can be found either on Blackboard or in my math lab, and turn to page 9 in the chapter 7 handout, and we'll go and get started. So the first thing that goes along with dealing with the normal curve is the idea of what's called the standard normal curve. So suppose that the random variable x is a normal distribution with mean mu and standard deviation sigma, then the random variable capital Z is equal to x minus mu over sigma, and is normally distributed with mean equal to mu equals 0 and standard deviation of 1. The random variable Z is said to have the standard normal distribution. So when we're using the normal distribution and we use Z instead of X, when we use letters Z, either lowercase or capital Z, we're referring to the standard normal distribution, which we're saying that mu is 0 and sigma is 1. When we use X, we're referring to any random variable normal distribution. So one thing we can do is we can normalize individual values from a random variable x onto z. And the way we do that is by using the z-score calculation, which is what we have up here. So if I wanted to know what is z1 given that x1 is 18, I would do z1 equals x1 minus mu over sigma. Okay, so in this case, that would be negative 7/6 negative 7/6, which is negative 1.167, rounded to 3 decimal places. Similarly for Z2, we do the same thing, right? Z2 would equal 30 minus 25 over 6, which is 5/6, which is 0.833, rounded to 3 decimal places. And so what we can show here is that x1, between x1 and x2 and z1 and z2, they would have the same area. So if we've got our x curve here on top, our mean was 25 with a standard deviation of 6. So 31 would be right here, 37, 43, right? We talked about how to do this in the last section. We just add the standard deviation going to the right and subtract it going to the left. So subtract 6, and you get 19, 13, and 7. So what we noticed in the last section is what we can do to talk about area is we can draw vertical lines at each of the data values. So here's 18 is about right here, and 30 is just inside of 31. And then the area between them is this area in here in the middle. Well, if we go to the standard normal curve, so here's our standard normal curve. We have a mean of 0 and a standard deviation of 1. So these would be 0, 1, 2, 3, and then negative 1, negative 2, negative 3 on the left. And so then if we mark in our z values, which were z sub 1 was negative 1.167, and z sub 2 was 0.833, negative 1.167 is just a little bit to the left of negative 1, and 0.833 is just a little bit to the left of 1. And so notice that those two regions match up, so the area between Z1 and Z2 should be 0.6760. Okay, so we're going to use this standard normal curve in a lot of different ways throughout this idea, but the key takeaways here that we'll practice a little bit more with in a second are that Z tells us to use 0 and 1 for the mean and standard deviation respectively, and that we can standardize any random variable down to the standard normal distribution, which is how you used to find these areas. Back in the day, the way you would find these areas is you would have a big book of tables, which would tell you the area under the normal curve, the standard normal curve. And so you would standardize your normal curve to that so that you didn't have to always do the calculus, because that's how you find these areas under a curve, is by using calculus. It's using integrals. So you don't have to do the integrals. Instead, somebody did them ahead of time and it's in a big book. Nowadays, we have calculators, so we don't have to worry so much about this standardizing the normal curve, but it is something we're going to use every once in a while, so we need to mention it. So let's practice using what we're going to do on the calculator by doing these with these standard normal curves. Okay, so if we bring up our calculator on ClassCalc, we're going to go to Stat, Distribution and Plot, and we're going to just choose the normal distribution. And then it's going to ask us for two things, the mean and the standard deviation. So with the problems on page 10 in your note sheets, we're all of them involve the letter Z, which means I'm going to put 0 in for the mean and 1 in for the standard deviation. And then we can zoom in on it. Okay, so remember, that is one of the more important things here is when we're doing these, is that anytime we're dealing with Z, our normal distribution will have a mean of 0 and a standard deviation of 1. Then what you can do is you can just use the CDF and PDF functions. In this case, we're pretty much only going to use CDF to find the areas in the same way we found them before. So if I want to do the area to the left of negative 0.43, so negative, that would be about here. And so I'm doing area to the left, so I want to go less than that. Okay, so what I can do is I can pull up CDF, and then I can notice that it fills in the whole graph. So right now I'm finding the area of the whole thing, which it's telling me is 1, which is what we expect. And so I can kind of just guess and check and see which one gives me area to the left. If I put it over here on the left, if I put negative 4.3, notice it's shaded to the right. So that's not right. So let's put it on the other side. So negative 0.43. And that's what we expect, because we want the x values that are less than negative 0.43. And if you wanted to, you could change these to be less than or equal to, but it's not going to change our answer in this case. Notice, which is something I guess I just learned about this, that you could use in the previous section to do less than or equal to in the previous chapter. But anyway, in this case, we get an area of 0.3336. Right? So an area of 0.3336. Okay. So now what we can do is the same idea, just now we want to find the area to the right of negative 1.53. So that was area to the left. So we already saw that if I put it on the left-hand side of my inequality here, I get area to the right. So if I put in negative 1.59 over here, notice it's shading to the right of that value in the graph. And so that gives us a value of 0.9441 when we round to 4 decimal places. Okay. And then we could do area, right? So that one. So then we can do area between, which means we're just going to put this left value on the left and the right value on the right. So negative 1.04 to up to 2.76. And notice in the graph, we're shading between those. So here's negative 1.04 and 2.76 is over here. And we're shading in between those. And that gives us 0.8479 when we round to 4 decimal places. And now the last one here, they're asking us to do the area to the left of z equals negative 0.24 or right of 1.2. So we're actually going to do outside of this area. So it's the same idea as what we did here, except we want to do outside. Okay, so what we're going to do is we're going to put in our values, which is negative 0.24 to 1.20. So we're doing the area between those, but I don't actually want the shaded region, which is this number. What I want is these regions out here. Well, what do we know about the area of the whole curve? Well, the area of the whole curve is 1. So we can do 1 minus this number. So it would be 1 minus 0.4798 if I round to 4 decimal places. So we do 1 minus that. Okay. And so we can just plug that into our calculator. and we get 0.5202. Okay, so that's the idea of how to do these. Okay, so normal distribution, because we're looking for z values, we put in 0 for the mean and 1 for the standard deviation, and then we can just plug in the appropriate inequalities. So what I'd like y'all to do now is practice doing this on your own. So using ClassCalc, find these areas. And when you're ready, go hit pause, and when you're ready, hit play, and we'll go through them together. Okay. Let's see. Whoops, that didn't do what I wanted to do. Let's try this for a second. Nah, I don't like that. Okay. Let's just put it. Okay, so for these ones, we're going to use 0 and 1 again, right? Because we're still doing this with z values, so we're going to be on the standard normal curve again. So I can just use this graph. The graph's not changing. All that's changing are the z values. So to do the area to the right of 1.78, I put 1.78 on the left side of my inequality, and I get rid of what was in there before. Okay, and see it's doing area to the right of 1.78, so that's 0.0375. Then if we want to do area to the left of 2.9, we put that on the right side of our inequality because we want x to be less than. And we get 0.9981 for area to the left of 2.90. And if we want to be between negative 3.03 and 1.98. We can do that. Put the left endpoint on the left, the right endpoint on the right, and we get 0.9749. And then if we want to be to the left of negative 1.56 or to the right of 2.56, we put those in. We get the area in the middle, which is 0.9354, and then we're going to do 1 minus that because we want to be out here, to the left out here, or to the right. So we're going to do 1 minus that. So here's the answers, and then I'll do 1 minus for the last one and put that answer up. So 1 minus 0.9354 is 0.0646. Okay, so that's the idea of what we're doing here. With these problems. So now what we can do is, that's how you find the area under the curve. Another thing you can do is find the area, find the z-score that goes with an area. So this first one says, find the z-score such that the area under the standard normal curve to its left is 0.2. So we're still on the standard normal curve. So we're still using this graph. Let me get rid of what I have here for now. Okay, let's clear this, get rid of it. Okay, so we're still looking at this, but instead of trying to find the area under a given value, we want to find, like if I wanted to try to find the area to the left that is 0.2, I could just start putting in random values and see if I get it. So like I could put in negative 1, and that's 0.28, so it's going to be a little bit to the right of that. You know, I could do like that. There I went too far. Negative 0.9, that's too far to the left. And notice I'm vacillating around 0.2 as an area. So what we can do is we can add a function to our normal distribution. So if we go back into stat, distribution plot, one of these things says inverse CDF, dot inverse CDF. Okay? So if I choose that, what it'll allow me to do is it'll allow me to find areas to the left and to the right. So what we can try doing is try putting in 0.2. Okay, and it'll tell me then that the value that will give me the area to the left is negative 0.841. And if we check that, if I put in negative 0.84162, right, it's very close to that, and I rounded it off, so it's not going to be exactly what I was looking for. Okay, and so that's how these work. Okay. Okay. And so what you have to do is you have to add it on to the normal distribution you're already dealing with. Now, this inverse CDF, so what this would look like, the command for this is normal distribution, your mean and your standard deviation dot inverse CDF, and then you put in here the area to the left. Okay? So if I want to do any other area, such as if I want to do area to the right, well, let's draw a curve here for this one. So I want area to the right over here, which is 0.35. Well, how much area is there to the left? Well, we know there's 1 is the total area, so the area over here would be 1 minus 0.35. So we can do the same command we just did, except this time I'm going to put in 1 minus 0.35. And this time it'll tell me that the data value is 0.3853. Okay? So that's the idea of how this works. Okay. So that's if I want to do left or right. But now if I want to do, let's say they want us to do that 99% of the data is in the middle of this, so 99% of the data is in the middle. So then the question is, how much data is over here? And how much data is over here? Well, there's 1% in the tails, but I have to divide that in half, right? Because there's 2 tails. So that's 0.5%, which equals 0.005 of an area. Okay, so I would do the same thing I did here, except I'm going to put in 0.005, which tells me it's negative 2.576. And then if I want the data value on the right, I need to add 99% to that. Right? If I want the one on the right, I need to add here, over here is 0.005. So then this line over here would be 0.995. So we put in 995, and it gives me 2.576. Okay, and so that's the idea of how this inverse CDF works. Okay. Now, we can also use this. There's another term that's definitely going to come up later called Z sub alpha. So this is a very special area under the normal curve. That's down here at the bottom of our notes. So Z sub alpha is something we're going to use in upcoming chapters. And it's simply the z-score such that the area under the standard normal curve to the right of Z sub alpha is alpha. So that this area to the right is that. So we already just talked about how to do area to the right. So to do area to the right, we would, but I'll write it down here. To do this, we do normal distribution, comma 0, comma 1, dot inverse CDF, and then we put in the area to the left. Well, the area to the left, to the right, the area to the left would be 1 minus the area to the right, so 1 minus alpha. So if I wanted to find Z sub alpha, Z sub 0.05, I would do exactly what we were doing here, except I would put in 1 minus 0.05. And it would tell me that z sub alpha is 1.645. Okay. So the next one, I would do the same thing at 0.01. So now instead of 0.5, I would put in 0.01. So that one's 2.326. And then the last one was z sub 0.35. So we put in 0.35, and we get 0.385. Okay. So that's the idea of how z sub alpha works. Because it's area to the right, you just do 1 minus the area to the right, and that gives you the area to the left that we can plug into our function on our calculator. Okay, so that's all we're going to talk about, the standard curve. But now we want to be able to apply this to any normal curve. So that's what we're going to do here. And the nice thing about using our calculator is it's set up really well to do this, because we can make any normal curve using the function on our calculator by simply doing normal distribution and putting in our mean and standard deviation. So the reading speed of a 6th grade student is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. So we can put in 125, comma 24 into our calculator. So if I get rid of this inverse CDF, because I'm not going to use that right now, and I change my mean and standard deviation to be 125 and 24, and then we zoom in on it because it's not showing up in my graph because I'm nowhere near that mean. Notice I basically get exactly the same graph I had before. It's just been shifted and moved, and these values are different along the bottom. Okay, so there's our normal. So we can use CDF to find probabilities, right? So if I go back to the problem, it says, what is the probability that a randomly selected 6th grader reads less than 100 words per minute? So that's the probability that x is less than 100. So less than 100 would be the area to the left of 100. So we want x to be less than 100. So I put 100 on the right, and notice it's shading less than 100. And so we get a probability of 0.1488. So there's about a 14.88% chance that a 6th grader reads less than 100 words per minute. Okay. So then what's the probability that a randomly selected 6th grader reads more than 140 words per minute? So that would be the probability that x is greater than 140. So that would be the other direction, right? That would be over here on the right. So I put it on the left because I want x to be bigger than 140. And remember, with inequality symbols, the bigger thing is always on the mouse side of the inequality. So in this case, I want x to be bigger than 140, so x needs to go on the mouse side. So that's a 0.2660% chance if I round to 4 decimal places. Right, so there's about a 27% chance that a 6th grader reads more than 140 words per minute. And then if I wanted to do the probability that they read between 110 and 130, right, that's really the easiest of these, right? Because if it's between, I just put in the lower bound on the left and the upper bound on the right. And notice it's shading in between 110 and 130. And there's about a 0.3165 chance that a student is reading between those numbers, right? That's the area of this shaded region. And then the last one says, would it be unusual for a student to read more than 200 words per minute? So to find out if something is unusual, remember what we want to do is we want to find out if the probability of that is less than 5%. So we're going to go in here. We're doing to the right again. We want x to be bigger than 200, so 200 is less than x. And so we get 0.0009 if we round to 4 decimal places. So the question is that less than 5%, 0.05? And the answer to that is yes, that's true. So it is unusual. Okay. And so that's the idea of how you can use normal CDF to find probabilities on any normal curve, not just the standard one. So go ahead and flip over to the next page, pause the video for a second, and try these. Okay, so now that you've had a chance to try these, let's run through them together. So we're just going to start off by changing our, let's clear this first of all, changing our mean and standard deviation. So our mean here is 25, and our standard deviation is 0.07. Okay, and then I'm going to hit CDF. Oh, not CDF. I'm going to zoom in so we can see our graph. So there's our graph. Okay, now we can do CDF. So what proportion of rods has a length less than 24.9 centimeters? So the probability that X is less than 24.9. So we want X to be smaller than 24.9, so we're going to put the 24.9 on the right. And it shades that region, so we did it right? We want to be less than that. So that probability is 0.0766. Okay. So that's the first one. Then the second one says any rods that are shorter than 24.85 centimeters or longer than 25.15 centimeters are discarded. What proportion of rods will be discarded? Well, so that means we want to find the probability that X is less than 24.85 or more than 25.15, which is the same thing as 1 minus the probability of being between those two. Right, so that's what we're going to put into our calculator. So we're going to do 24.85, and then we're going to go up to 25.15, right, like that. And then I think we could actually do 1 minus, and then if you double click on this, it would on your phone. It's not working here, but anyway. So just go ahead and do that in your scientific calculator, or if you're grabbing these on your phone, that should work what I just tried to do there. So 1 minus 0.96787 is 0.321. Wait, 0.0321. Okay, so like about 3% of all rods would get discarded. Okay, so those first few problems were pretty straightforward. These other two may have been more challenging. So let's go ahead and look at this. This asks you to expand beyond what we just did. So if 5,000 rods are manufactured in a day, how many should the plant manager expect to discard? Well, if 5,000 are made and this proportion are discarded, we can just multiply those to figure out how many are discarded. 5,000 times 0.0321, which is 160.5, which we could round up to 161 rods. Is how many he should expect to discard in a day. Okay, and then to expand beyond that further, if an order comes in for 10,000 steel rods, how many rods should the plant manager manufacture in order if the order states that all rods must be between 24.9 centimeters and 25.1 centimeters? So this is similar to what we did up here, but we don't know this. We don't know this number. We know something to do with this number over here. So what we want to know is how many rods do we have to make to keep 10,000 of them? So what we're actually going to want to do is we're going to take the number of rods we need to make, which is X, times the proportion that we're going to keep, which is all the ones that fit this description. So 24.9 is less than or equal to X, which is, or less than, or equal to X, which is less than or equal to 25.1. And that should equal 10,000. So we should just be able to divide by whatever this probability is. So let's find that probability first of all. So what is the probability of being between 24.9 and 25.1? That probability is 0.8469. Okay. And now we're just solving an algebra problem. So divide by 0.8469. So X is 11,807.8, and then we would want to round that up, and you'd always want to round it up because you need to overestimate, right? If you round down to 7, you'd probably end up with 9,999 rods instead of the 10,000 you actually need. Okay, so that's the idea there. And then on the next page, I just want to point one thing out here, which is I don't think we're going to do all these. It occurs to me that I didn't make this exactly the way I wanted, but I really want to just talk about this idea of percentile rank, because these first two problems are just like what we just did, right? So if I go ahead and put in my mean and my standard deviation to get my curve here, so we're doing a different one again, so go ahead and get rid of that information, put in your new mean and our new standard deviation. And if you want to see the graph, you can zoom in on it. There's our new curve. Okay, so then we want to know what is the percentile rank of an 18-ounce bag of Chips Ahoy that contains 1,475 chips. So what you want to remember is, what does the word percentile mean? So percentile means percent of the data to the left. So if I want to find the percentile rank, what I need to do is I need to find the probability that X is less than 1475. Right? I need to know what proportion of the data is to the left of 1475. So we can just put in X is less than 1475. And what we get is 0.964. And so what percentile rank is that? What percent of the data is to the left of 1475? 96%. So this would be in the 96th percentile. And then you could do the same thing for the bottom one, right? And what's the percentile rank of a bag with 1,050? So for that one, we do the probability that X is less than 1,050, which is 0.036. Okay. So what percent of data is less than that? Well, 3%. So that would be the third percentile. All right, because in this case, I need to round down because I want to know what whole percentage is less than that. Well, it would be in the third percentile because 3% of the data is less than it. So that's just one other way to use this normal CDF. But we can also do this inverse. If we know an area, we want to deal with, we can work backwards to find the data value that goes with it. So in this same problem, the number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate chip cookies is approximately normally distributed with a mean of 1,262 chips and a standard deviation of 118 chips, right? That's what we were just dealing with. Determine the 30th percentile for the number of chocolate chips in an 18-ounce Chips Ahoy bag. So 30th percentile, remember, means 30% of the data is to the left, right? So we're going to do this exactly the same way we did some of the problems in previously. We can do what we have up here, but now we're going to put in our inverse CDF, which I'll just show you where it is again. So go down to your menu, choose Stat, choose Distribution and Plot, and choose Dot Inverse CDF. And then you can just put in the area to the left, which in this case is 30%, which is 0.3. And so what we find is we get 1,000.12, so that would be 1,200 would be the 30th percentile. Okay. And if I want to determine the number of chips in a Chips Ahoy bag that make up the middle 99%, just remember from what we did earlier that if 99% is in the middle, then 1% is on the outsides. So that means over here is 0.005 and over here is 0.005. To find the number on the left, the area to the left is just that, 0.005, which gives 958. But then to do area to the the other one, I have to do area to the left again, which is 99 plus 0.5%, which is 0.995, which would be 1566 if I round to the nearest number of chips. Okay, so that's just using this inverse CDF idea, but now with a different mean and standard deviation. So to finish off this section, go ahead and pause the video, try these two problems at the bottom, and then we'll go through them together. Okay, so now that you've had a chance to try them, what is the reading speed of 6th graders whose reading speed is at the 90th percentile? Well, we can get rid of what we have here, and we can put in a new normal CDF, normal distribution, with a mean of 125 and a standard deviation of 24. And then we can do our inverse CDF, right? So distribution plot, inverse CDF, and put in our mean. In this case, we're doing the 90th percentile, so that would be area to the left is 0.9. So the 90th percentile is 155.8, which is 156 when we round. And if we wanted to do the middle 95% of data, similar to what we did above with the middle 99%, but now we've got 5% on the outside, which would be 2.5% over here and 2.5% over here. So for the one, whoops, sorry, I didn't bring this up. So here's my drawing. So we've got 95%, so that's 5% on the outside, half on each side, so 2.5% on the left, 2.5% on the right. So to do the one on the left, I just put in 0.025, right? 2.5% is a decimal, and I get 77.96, which is 78. And then to do the one on the right, I'm going to add 95% to that. So 95 plus 2.5 is 97.5, so 0.975. So that's 172.04, which is 172. Okay, so that is it for this time. Thank you for watching this video lecture, and make sure you're doing your homework and all that. If you have any questions, feel free to send me a remind message or an email, and I'll get back to you as soon as I can. But I'll see you for the next video.